We are about to start to talk again about the universe.
Unified field theory, basically.
I give the floor over to Dennis.
I'll just skim through what we did yesterday for the benefit of people who weren't here. We basically found a whole new set of spaces. These are spaces with geometric structure. They have rotation matrices, they have trigonometric functions, they have distance functions within them. We found these by picking out terms of the exponential series using the finite groups. Used the finite group C2, we got two-dimensional space-time. With the finite group C4 in its two-dimensional representation, we got the complex numbers, the Euclidean space. We found three-dimensional complex numbers, the three-dimensional complex plane, using the group C3 and three representations, three-dimensional representations of the order 6 group C6. So we've got an infinite number of different types of space, all of which have got rotation matrices and all the attributes of a geometric structure. We then found that if we took the superpositions of these, one unique space came out, and that unique space is a superposition of both left-hand and right-hand four-dimensional space-time. So within the exponential function there is all these infinite number of geometric structures, and one of them, just one, is a different type of space, a superposition space, and it's the only one that has geometric structure. What we're going to do now is we're going to adopt some of the ideas of gauge theory. According to gauge theory, the electron has an internal symmetry space, and the phase of that space varies from point to point over four-dimensional space-time. The internal symmetry space is nothing more than a set of commutation relations, in fact S2 in the case of the electrons. And gauge theory is done with Lie groups, where the internal symmetry space is nothing but a set of commutation relations. What I'm going to do exactly the same idea, but instead of using the internal symmetry space, the Lie groups, I'm going to use the spaces we discovered within the exponential function, these that have rotation matrices. And so we can actually vary the phase in a meaningful way in these spaces. That's the idea behind it. What we're going to do, we're not going to quite do it the same as gauge theory. We're not going to form Lagrangians and differentiate them to get Euler-Lagrange equations. We're just going to take the gauge space as being a potential. We could call these potential spaces. We're then going to differentiate the potential to get the fields. We will then differentiate the fields to get the equations of motion. These spaces are non-commutative. We will have to differentiate non-commutatively. And I'm going to show you how I believe non-commutative differentiation should be done. Now this afternoon, Leo Kaufmann is also doing something on non-commutative differentiation. I've read his paper. I don't thoroughly understand it, but I think it's basically barking up the same tree as I am. We both use the commutator as a differential, but the difference seems to be that I also use the anti-commutator, whereas Leo uses only the commutator. When you differentiate non-commutatively, you're forming the differential, which is dy times 1 over dx, or 1 over dx times dy. So you get two differentials, and this is why we're going to get two fields out of each potential. Right. We've done that. Right. The actual way we differentiate is the classical way that you do it by taking limits and all that kind of stuff. But in actual fact, it turns out you get exactly the same results if you adopt the idea of a differential operator. Now, differential operators don't actually exist, they're just a shorthand of notation, and they do things very easily. And basically you form a differential operator, or in this case dy by dx, dy's and dx's, and you multiply them out like matrices. So this means differentiate f by dx and differentiate g by dy for that position there. And there we just differentiated a complex number. When we come to form the commutators, we're going to differentiate on both sides. So all these differentiations do work in the classical way, taking limits. We're just using differential operators because they're easier. If we do it with the complex numbers, we get curls, we take the exponential curls, we see the curl is an angle within the rotation matrix. Two-dimensional space-time, again, we apply the operator. Two-dimensional space-time is commutative, so applying it on the right or the left gets the same results. And again, we get the curls come out of it. So we're differentiating the potential, we're getting curls and divs come out of it. Let's do a three-dimensional one. This is a three-dimensional space that we found.
Could you point at the screen?
It's
more of an integrated
sorry,
feel about it.
Sorry, right, this is your differential operator, and it's going to operate on this matrix by simple multiplication. That's going to multiply that to get that point there. What we get out of this is three-dimensional curls. By three-dimensional, I mean we've got three variables here. We've got A's, B's and C's. Whereas the other one, we have two-dimensional curls. We're going to try and organise the camera here. What we've got, we've got one of these spaces. This is three-dimensional space. It's not like any three-dimensional space we've ever seen before. It's straight out of the exponential function by taking the third terms and combining them rather than taking every second term, which is what we do to get the sines and the coshers. So it's just splitting the exponential series and we're getting all this geometric structure. We're putting that as a potential, we're differentiating it, we're getting the curls and we're getting a divergence down the real axis. These can't fit into our four-dimensional space-time because our four-dimensional space-time cannot accommodate three-dimensional rotations. The three-dimensional distance function, held invariant by three-dimensional rotations, cannot be accommodated in our four-dimensional space-time distance function. So we'll never see these. But this is exactly the same as what we've done with the complex numbers, which were two-dimensional and where we get the curls, two-dimensional curls from. Now we're going to do non-commutative differentiation. Because it's non-commutative, 1 over dx times dy is not the same as dy over 1 over dx. That's why we're going to get two differentials. This is the differential operator of the quaternion. It's got exactly the same layout as a quaternion. These are the real axis down here, these are the I variables, these are the j variables, and these are the k variables. Where you put the minus signs is really a matter of whatever you want. It determines the direction of the force. It's just an arbitrary direction on the axis. Basically, I just reverse them all and everything is consistent. As long as it's all consistent, you can put them anywhere you want. That's what I've defined to be the differential operator. The only definition is where I put the minus signs. This is a left-handed quaternion. The left-handedness is in the distribution of the minus signs in the bottom 3 by 3 right-hand part of the matrix. And we're going to differentiate left-hand quaternions with this. There we have a left-hand quaternion potential. It's a quaternion, it's exactly the same, real part down there. We've got 5 for the real part, and we've got AX's and AY's. It's a vector, it's a quaternion, and you can look at it as a vector. And we're going to form two differentials. These are called the E differential and the B differential, after the electric field and the magnetic field. These are going to give the kind of curls that we get for the electric field, d phi by dx minus dx ax by dt. There's a t in them. They're going to accelerate particles. These are going to form differentials like the spatial curls, like the magnetic field. So we're going to get two fields because we're non-commutatively differentiating a non-commutative potential. Now here we just do it. We get the divergences down the middle, and we see we get two-dimensional curls. Now the reason we get two-dimensional curls is because we actually get four-dimensional curls with the first part of the differential operator. This will give us a four-dimensional curl. This will give us a four-dimensional curl. When we add them together, they cancel and we get two-dimensional curls. And the same with this. When we subtract those, they cancel to get the other two. It turns out the four-dimensional curl. So we've got two-dimensional curls. Because these are two-dimensional, and because our four-dimensional space-time accepts two-dimensional rotations, these can be manifest as forces in our four-dimensional space-time. They turn out to be the electron and the neutrino. Well, I take them to be electron and neutrino. We have a B field. We've done the left-hand ones. We've also done the right-hand ones. There's a difference in distribution of minus signs in the bottom and also at the top. So we're differentiating the fields to get the E fields and the B fields. Now we're going to deal with the neutrino mass problem. I'm going to take the view that the B field differential of the quaternion potential is the neutrino. We have here the formula for calculating the probability of neutrino oscillations. What I wish to point out is that this is frequently wrongly written. It's written as delta M, and you get the feeling that it's the difference in masses of the neutrino from that notation. It's not. The actual formula is the difference in mass squared. So, because neutrinos oscillate, we know that they have a squared mass. People have always assumed that means they have a mass. But they don't have a mass because they travel at the speed of light. So we've got a neutrino that does not have a mass, but it does have a squared mass. What kind of a field could possibly, now mass is a real part, a real number, what kind of a field could possibly have zero real part, but when squared becomes massive, gets a real part? It could be a complex number. It could be just the i's without any real part. You take the I, you multiply it by its conjugate, and you get a real number. So you've got mass squared. But complex numbers are not left-handed. Neutrinos are left-handed. So it could be a left-handed quaternion field. It turns out it's a bit more than that actually. It's a superposition of both quaternion fields. Right. And that's it. We've just squared the B field. It's B, we use letter B because it's like magnetism. That's what you might call the magnetic energy. So though the left-handed B field had zero real part, zero mass, it does have non-zero mass squared, and that fits the observation. So that's a stab at explaining the neutrino mass oscillations. Right, in electroweak theory we have the concept of a right-handed electron and a left-handed electron. The idea being that if electrons are massless, they travel at the speed of light. If they travel at the speed of light, then you cannot overtake them to turn what would be a clockwise spin into an anti-clockwise spin by looking back at it. The left-handed electron and the right-handed electron are then taken as a superposition to form the electron. That's the idea of electroweak theory. We're going to do basically exactly the same, but our electrons are going to be quaternions. We've got a right-handed electron field, we're going to get a left-handed electron field, we're going to get a right-handed neutrino field and a left-handed neutrino field from differentiating the right-handed quaternions and the left-handed quaternions. Two fields from each. And we're then going to form the superposition by adding the left to the right. This field, the superposition of a right-handed neutrino and a left-handed neutrino, is a left-handed field. We've predicted that the neutrino will be left-handed. The same applies to the magnetic field when we do classical electromagnetism. So out of this, it's rather an amazing thing that you can get a right-handed neutrino field and a left-handed neutrino field, and the distribution of minus signs is such that when you take the superposition you get a left-handed field. But that's simply the way the minus signs are distributed. I do assure you I checked the minus signs many times. So we began yesterday, we know more than the real numbers. We've found a left-handed field inside the real numbers. If the real numbers exist, so does this left-handed field. Because the curls are two-dimensional, this left-handed field can be manifest in our four-dimensional space-time. We're going to do a little electroweak theory. It's not classical electromagnetism. Classical electromagnetism is basically pretty much the same as this, but it comes out of the finite group D4, the four-dimensional representation of the finite group D4. That's the same group that we got four-dimensional space-time out of, and we're also going to get gravity out of it. It's going to come alongside classical electromagnetism. This is the Maxwell equations that govern the electron and the neutrino. We differentiate the fields. We've got the fields. We differentiate the potential to get the fields. We've got the fields. We're now going to differentiate the fields. And we're going to differentiate them non-commutatively. There are two fields. We've got a right-hand one and a left-hand one. Whipping through all the different fields. Basically, we're just going to differentiate fields, and then we're going to take the superpositions of the left-hand fields and the right-hand fields. We're just going to add them together. When we do that, we get a set of curls. These are the kind of curls you see in Maxwell's equations, dV by dx and all the rest of it. That's the kind of stuff that comes out from the fields. We just go through the process. Yep, that's some. We then take the superpositions. We form the superposition fields by simply adding them. That is the superposition of the B field differentials, and that is we take to be the electron. This we take to be the neutrino. Oh, sorry, I got that mixed up. This set of curls here, and we've got a set of curls here. Now we assume they're going to be a left-handed quaternion. I'm not quite sure how I can justify that assumption, but it does produce the Maxwell equations. Why does it have to be a left-handed quaternion? I don't know. But when we do that, we get these Maxwell's equations, inhomogeneous Maxwell's equations, and we get the homogeneous Maxwell's equations by the same, by taking the superposition and by assuming they're going to have the structure of a left-handed quaternion. These equations have SU2 for the commutation relations because it's the quaternions. The classical magnetism, electromagnetism has SO3 the Lorentz group. The inhomogeneous Maxwell equations come out by the same means. We just take the differentials of the fields and we form the superpositions, and we get again an electron and again a neutrino. Superimposing the superpositions gives us and assuming a left-handed quaternion gives us the inhomogeneous Maxwell's equations. We've just substituted the x by dt, the j's and the y's, and that's just for simplicity. So what we've discovered that within the quaternions we have the Maxwell equations. These are the equations of motions of a quaternion potential that varies locally over space-time. And we think that is the electron and the neutrino. There's a few differential identities associated with non-commutative differentiation. Within the concept of antimatters within the quaternions, within the two-dimensional space-time, you cannot have negative entities equal to the cosh. The cosh just does not have a negative value. The sines do, sines and cosines. The antiquaternions also have that negative entity, so you form your antiquaternion simply by reversing every single minus sign. These will give you right-handed neutrinos when you differentiate them. So there is antimatter within that. We now see why there are two electromagnetic fields, electric magnetic, electron, neutrino. It's because there are two differentials with non-commutative potential. It's also because there are two types of rotation in our four-dimensional space-time. Right, so you'd think, we're coming on to gravity now, you would expect two gravitational fields. All fields come in pairs, and in part of the predictions of this is that quark fields will have neutrinos associated with them. Quark neutrinos have never been observed. but you wouldn't expect them to be. Why is there one gravity field? Well, we're not going to go through all the differentials. It's pages and pages of matrices. But when you do, you differentiate the 6 four-dimensional representations of the dihedral group D4, and you get 6 B fields, 3 left-handed, 3 right-handed. You take the superposition by adding these fields together, and all the B fields cancel. You get a big fat 0. They're the 6 spaces, the 6 representations of the D4 group, left-handed and right-handed, 3 of each. They're the ones what we're going to assume as potentials. We differentiate them, we form the superposition of the B fields, and we get a big fat 0. So your second gravitational field, your gravito-magnetic field, has just vanished into thin air. You're left with one gravitational field. But the magnetic energy of that gravitational field doesn't cancel. The energy of the field is given by simply taking the inner product with its conjugate. That's the energy of the gravito-magnetic field. When we take the superposition of these, it's non-zero. And so, if energy gravitates, we have some kind of gravitated entity throughout the whole universe that does not correspond to a field. It sounds exactly like dark matter. And so, quite possibly, we seem to be able to predict dark matter. So we've solved the neutrino mass problem and predicted dark matter, it seems. We come on to quarks. The quark forces can only be manifest in our 4-dimensional space-time if they have 2-dimensional curls. The quarks come out of 8-dimensional representations of 16-dimensional groups. They're all connected by the inner automorphism group C2 cross D2, the Klein group that Peter mentioned. But they come out as 3 of them, but 2 are isomorphic. So you've got 3 quarks, 3 quark neutrinos, but they come out as 4-dimensional curls because they're 8-dimensional fields. When you differentiate a non-commutative field, you get half the size of, say, an 8-dimensional non-commutative field, you'll get 4-dimensional curls. But when you take the superpositions of the 4-dimensional curls, they become 2-dimensional. And so you get 3 sets of 2-dimensional curls, but 2 of them are isomorphic, and so you're predicting 2 quarks. But one of them will probably have twice the electric charge of the other. Because it's an 8-dimensional matrix, and because of the nature of the algebras, I'll go into that in detail later, it splits automatically an 8-dimensional force into 4 4-dimensional forces, which are the 4 blocks in the 4 corners of the 8-dimensional matrix. The reason it does this is because basically all the algebraic spaces we've been talking about, all the geometric spaces we got out of the exponential series are basically Clifford algebras. But the Clifford algebras without the concept of bivectors or trivectors. The Clifford algebras done algebraically properly without any of the redundant concepts. And 8-dimensional Clifford algebras have a commutative variable, which is normally taken to be the trivector. And so you've effectively got 2 identities in an 8-dimensional Clifford algebra. And in what we're using, we've got 2 identities, and that's what splits the 8-dimensional force into 4 forces. So we'd expect 4 forces, electromagnetism and 3 colour forces. So we seem to be predicting the quark forces. I haven't got very far with the quarks. It's a lot of calculation, and I haven't quite done it. There's a mistake on here. So what we're actually predicting for the content of the universe is a left-handed electron and a right-handed electron. And that should be a right-handed neutrino rather than left-handed neutrino. It's the superposition that's left-handed. We're predicting a left-handed and right-handed, and there's 2 quarks, and they've got neutrinos with them as well. I don't know about the handedness. That's slightly different from electroweak, where they just don't have a right-handed neutrino. That's pretty in electroweak. And so we've got a match between the 2-dimensional curls and the Fermi content stroke force content of the universe. We've got a unified field theory. It's not unified in that it's one force, it's different forces, but there's a mathematical unification. And all we're doing is we're just digging spaces out of the exponential series, floating them as potentials over the four-dimensional space-time, which also falls out of the exponential series, and differentiating them. And it's as simple as that. There are implications for physical constants. Within two-dimensional space-time, we've got the t's and the z's here. C is just a scaling factor. It scales time, seconds against meters. Within all of these spaces there are similar scaling factors. And though we've not gone into it at all today, when you actually calculate the different representations of the groups, you do it by putting these scaling factors in and enforcing multiplicative closure, and that gives you all the representations. It seems that these scaling factors are the physical constants. If that's true, and it certainly seems to be, then all these physical constants are tied together by algebraic relationships, the kind of thing that expresses the fine structure constant. I think it's is it E squared or a C? There's a C in it, an E in it, and a Planck's constant in it somewhere. So what we've got is constant, not constant numbers, but constant algebraic relationships. Imagine the complex plane, and imagine I decide to scale the imaginary axes by 100 to 1. What you normally see in the complex plane is a nice circle, but what you see if you crush it down is an oval, an ellipse. But it's not really an ellipse, the mathematics hasn't changed. The circle's still there, it's just an arbitrary scaling. What this means for physical constants is that if one physical constant changes its value, then the other physical constants automatically change theirs in order to keep the physics the same. In the same way that the mathematics of the complex plane stay the same under arbitrary scaling, so the physics of the universe stays the same under arbitrary scaling of the physical constants. So the conclusion of that is we live in one particular type of universe that has one particular type of physics that derives directly from the real numbers. That physics is immutable, and no matter what values the physical constants take, we get the same physics. So the physical constants are really all values that you want them to be. It's the algebraic relationships that's constant. We'll look at the expanding universe a little bit. Within our space-time we have three copies of two-dimensional space-time. It's the hyperbolic complex numbers. This is the space of the hyperbolic complex numbers. It starts here, it expands spatially as it goes out there, and as time goes forward we get an expanding universe. The speed of light seems to be the gradient of this hyperbola. So back here at what we would call the Big Bang, the speed of light was infinite. The physics would be the same because all the variables, all these physical constants adjust appropriately to keep the physics immutable. But if we say, how many ticks of a cesium clock has there been since the start of the universe? Let's measure the age of the universe with a cesium clock. Let's suppose this cesium clock ticks once every billion years. And we look at it today, and yes, a billion years, and we take that same length of time it took to tick today, and we go back in time and we say the universe is 13.8 billion years old. But supposing the rate of ticking depends upon the physical constants, and it depends upon the speed of light. And we say, such that when the speed of light becomes infinite, the rate of ticking becomes infinite. And we say, how many ticks of the cesium clock have there been since the start of the universe? And the number is infinite. And so we get two views of the age of the universe. One is it's infinitely old, and one is that it's 13.8 billion years old. And it seems to have been 13.8 billion years old 100 billion years ago, and will be 13.8 billion years old in 100 billion years' time. I
was going to argue there's a third point of view, and that is that every instant is an echo, a reflection of the Big Bang, because the extent of time and the extent of space are derived from each other. So we can say that it's ever-present singularity.
Yeah, this is not a mathematical conclusion. This is me making assumptions about this being the speed of light. It's me making assumptions about the nature of time. But I think it would resolve the problem with the big anomaly at the start that the universe started 13.8 billion years ago. It ought to be infinitely old. If the scaling factors are the physical constants, we can calculate how many they are. I haven't quite got round to the quark yet, so I don't know for sure. But we will be able to actually calculate the algebraic relationships between them. That's it. And that's the end of the presentation. Welcome questions and comments.
Comments from the floor?
When you mentioned the commutator and the anti-commutator, is it really just a question of reversing signs?
Yes,
and orientation? Or is there something special about one or the other?
there's nothing there's no different. They are the two results that come out. So you can pull them back up. Where are they? Yeah. Yeah, the only difference is that sign there. Anti-commutators and commutators are used in particle physics all the time, of course.
Right. Anybody from Zoom? We can't see the whole. So I can't see. Yeah, if you could, because we can't see if somebody raises the hand. Okay. Any questions for Dennis? Okay. So, John, you are saying something, but you are muted. That's a standard problem with Zoom, of course.
You just go point to your ears. And you'll see.
I think John is trying
I
to
think,
say something.
You need to speak into the microphone for them to hear you, I think, possibly as well. I don't know how good the
yeah.
microphone
Are you
is.
saying something, John? We can't hear you.
Peter. Okay. Yeah.
You go ahead.
Okay. Well, at one point during the talk you said that you find these structures within the real numbers.
Yeah.
You made the argument that you find these structures within the real numbers and that they can be realized within four-dimensional space, therefore they must exist in four-dimensional space. Something like that.
The argument is that because our four-dimensional space-time can accept only two-dimensional rotations, it can accept only two-dimensional curls. And so we've got an infinite number of curls from these infinite number of potential spaces, but only some of them are two-dimensional. And they're the only ones that can be seen in our space-time as forces, and that gives us an exact match for what we see: the quarks, the electron, neutrino, classical electromagnetism, and gravity.
I just need to say I'm really sorry about missing yesterday. But did you send this out before? I mean,
I did, yeah.
So I could go and look, because I mean.
I think Barbara sent it round, but
I sent it to everybody.
if
So I know I received something, but I just didn't have time to look at it. And I thought I'd be here yesterday morning, but then I ran out of time.
What this is lecture notes, but I've got a paper that goes into all the details and it's lots and lots of calculations in. My email address, if you want to write it down, is Dennis, Dennis, 355, Dennis 355, at btinternet.com.
You can also get Dennis's books on Amazon. I have some of them, Special Theory of Relativity and Quantum Mechanics and stuff.
Well, if you just send me an email saying, send me some stuff over, I'll just forward it. You won't have to pay anything for it. I'll send copies of books and things. But this is actually done as a paper that was so long I couldn't get it published. It's 128 pages long. So I published it as a book.
I've got a sort of comment here about the age of the universe and so on. We project backwards and say it's 13.8 billion because of the way we do it. Now, if I remember, historically, Kelvin's first absolute zero of temperature wasn't zero at all, it went to minus infinity. His first temperature scale in which he had absolute zero.
I don't know about that, Peter. I'll take your word for that.
I think he did, and that reflects the fact that you can never get down there. And then later, he altered it so he got a linear relationship. And it strikes me that this is a kind of parallel to what we did with the age of the universe.
It might be, yeah. I mean, if we've got speed of light speeding up as it gets closer to Big Bang, then you've got something that's it could be a linear step, every step the same each way, and we get 13.8 billion, or it could be an infinite number of steps as it speeds up.
Yeah.
And so you would get two answers.
It could also be exponential, in which case it would never reach zero.
Yeah, I mean,
That's the nature, dual nature of time, is two different things.
I'm not arguing this particularly strongly because a lot of that is conjecture rather than what we've been showing you so far is
I mean, if you
mathematics.
think about the curve of an exponential or a logarithm function, you get a finite thing by integrating underneath it, but you technically have an infinite length of the curve itself. Because it's tending towards zero, so I think that's similar to what Peter says. We make an arbitrary choice to think of the speed of light as something that we tend to infinity in the classical model, and we make an arbitrary choice to think of absolute zero as not being something that you approach. But approaching logarithmically to zero is the same as approaching infinity.
I think Kelvin's first temperature scale was logarithmic.
Yeah, what it's really about is the idea of the universe starting 13.8 million years ago is ugly. It ought to be infinitely old. and it's simply that, it's just ugly to have it start.
Nah, you try and get rid of the Big Bang.
It also means you've got to make all kinds of strange assumptions to explain why the universe is flat. So you have to say there was this inflation suddenly after about whatever period of time, and it flattened it.
Well, we actually get inflation on that in two-dimensional space-time from the hyperbole. It seems to inflate on its own without any change of what they call it, some physical change.
So we're not noticing that it's inflating because we're moving along with it? Is that the idea?
I would think so, yeah. That's
So it
what I
looks
would
to us
inclined to think.
linear, but it might be just that it's...
I don't know, I mean, a lot of it's conjecture.
Yeah.
There does seem to be some mass in there. We do have 3 two-dimensional space-times in our universe, and two-dimensional space-time does expand. It is a hyperbola. So that does seem to explain the expanding universe. So there does seem to be some mass in it, but the idea that the universe is possibly infinitely old is conjecture, really.
You can also think in general relativity, Einstein's equivalence principle. You couldn't tell if you were sitting here in a gravitational reference frame or if you were in an escalator going up at a constant acceleration. So there's a way in which you might imagine that the Earth is constantly expanding outwards and folding in on itself as a dynamic process like a fractal would.
To make it look steady state.
Yeah.
Like it's,
Those are all models. I mean, I can call on Nick here because he put a very big table of possible models of the universe together with Mike. I'm not sure whether you want to add to that, but I will come back to that during my lecture. So it's just, for me, everything is a model, yeah? That's some seem to be working better, some worse, but as far as the age of the universe is concerned, I don't think anybody can give it.
There's a question there, I think it's Mike.
Yeah. Mike!
Hello.
Hello.
In Nicola's speech, thank you for that, Nicola, you pointed out that our current thinking somehow dropped off path of what Pythagoras was considering. The study of living systems probably falls outside of the current conversation and group here, and there is a statement by Maturana who says that in living systems there is no time at all. So maybe we should not be worrying about physical systems, quaternions and stuff all the time, but we'd occasionally move into the humanities and the non-physical world to answer these questions, which may shed light on the difference between, shall we say, the C.P. Snow science humanities discussion, argument, or hatred, overlapping vocabulary, etc., etc. Anyway, Maturana said there is no sense of time in living systems.
Okay.
Anybody come across this idea before?
Rilke talks about that. Rilke talks about animals. He talks about the way that we. I mean, he talks. You know, he writes about it in his prose, but also in his Duino elegies. He talks about the way the animals see that we human beings are kind of strangers in this world, and because of our thinking about time. Whereas for animals, they are there in their time, and there are not these questions. So that's, yeah. I mean, in a way, yeah, I mean, we are in between. We are in-betweeners. Humanity is, we are in between these, you know, this materials, you know, in the I-it, where we have some control over matter, but we are also in spirit, where we know our sense of ourselves as human and relating as human is a different way of being, and we are in this strangeness. And I think, yeah, I mean, these are very pertinent questions.
That brings me to think about the Japanese sign for king, which is like bar, and it is bridging the earth and heaven. Yeah. So we are the bridge between earth and heaven. We have feet on the ground, and our head supports the heaven. That's the another way. And actually, Chinese are very pragmatic. So that's
yeah.
Talking about time, Barbara, clock time for the moment.
Yes.
Have you got a substitute for Thursday where Roger Anderson was?
We are working on it because Sydney has to give.
If you don't have a volunteer,
Yeah.
my talk, which is on Friday afternoon, I could be persuaded to move it to Thursday at 10 o'clock UK time.
I object because people will come on Zoom and they want to hear you. Okay, we can sort it out.
Well, we could.
We can come to blows afterwards.
Or
Well, I would volunteer to do it twice. As
No,
you know,
no
with a
need,
bunch-
because
with a bunch
there
of
are-
slides, the slideshow emerges as we go along.
No, Mike, it's okay because it's we have other people who still want to talk, so we are alright. That's the.
Anyway, I'm flattered that there's at least one person who said they want to listen to me. Okay, thank you.
Yeah, no, we all want to. Peter is sort of raising his hand.
Your one about dark matter and so on. Now, something interesting, a Newton connection here. That he had a proposition 40. His book ends at proposition 42, book 3. But he drafted a proposition 43, which has never been published. And I have actually never seen it written out. I've only seen it referred to by other people. And in that proposition, he said, how do we know that the Tychonic theory of the universe isn't true? So in other words, how is it that we go round the sun goes round us and everything else goes round that? How do we know that? Because it always seems, I'm trying to work it out now. How do we know that the Tychonic theory isn't true? And he said, if it were true, there'd have to be another force which kept us, in the same position. And effectively, that's what happens. We think we're in the same position, but it's the inertia, and not another force that does it. And your kind of extra stuff is like kind of inertia, a fictitious force, a virtual force.
Don't do that. I'm not following that detail, I'm afraid.
Well, basically, you have gravity, and you have some bit extra that doesn't fit into gravity. Now, essentially, gravity generates an inertial reaction. And the inertia is like a kind of fictitious force. It's not a real one. It's not caused by something.
What comes out of this is two gravitational forces, a normal gravitational force that accelerates particles and another gravitational force that rotates, like the magnetic field.
Yeah.
But when you take the superposition, the gravitomagnetic fields all come to zero.
But gravitomagnetic really comes from inertia, not from gravity.
I don't really know where we might fit in. Not sure I understand inertia at all, to be honest.
No, I don't think people do, but I think that's what it seems to be.
Yeah.
An inertia being a fictitious force. It's as though gravity ought to have a magnetic component, but doesn't. But you know, it's sort of that ought to have is that kind of virtual, fictitious.
It certainly has in these calculations. It's just that it cancels. Perhaps at a quantum now, if you're doing quantum gravity, you'd have to split it down to the 6 individual forces rather than take the superposition. And possibly that's how you do quantum gravity. You just do it as individual forces rather than as a superposition. And classical stuff you do a superposition.
Newton's propositions 43 to 45 where he was trying to work out theorem of revolving orbits. So was the question of, you know, now we say that both the sun and the Earth they orbit around their mutual Barry centre,
yeah.
You know, mass times the distance. So he was trying to work out how you could have the moon orbiting around the Earth orbiting around the sun without the distance increasing, without the radial distance.
Basically, you were saying you've got to hold the Earth. If you're going to have moon orbiting around Earth, you've got to hold the Earth there.
Yeah,
you can, and then he solved it by realising they actually revolve around the baryocentric centre.
So Tychon the Tychonic system was a helio-geocentric. So it was you know, splitting the difference between the Copernican and the Ptolemaic.
Strictly speaking, ours is not heliocentric because it actually goes around the baryocentric, which happens to be in the sun.
So the baryocentre is both the geo and heliocentre, you know, summed together. So it's that's the superposition of these central forces to make the orbit stable, which again you only get in 3 dimensions.
But we think that we're stationary and everything moves around us. And it's a question of how do we know that that's not the case?
It's certainly the case. If I threw myself off of this building, I'd know I weren't stationary at some point.
May I sort of gently break the discussion because we need few minutes for Laurie to set up John's lecture. So we have to be sure that we get it empty. And probably you need to take the stick from the